Hi, you're on the Evan eCent channel again. This time we'll be talking about a lathe attachment designed to cut polygons. So that includes triangles, squares, pentagons, hexagons, octagons, whatever you like. This started with a YouTube video by MakeItExtreme exactly a year ago, where they demonstrated the building of such a machine or attachment, and they ran some videos showing the way the machine cuts the shapes. And although you could see the tool flying around all over the place, I could not make out how it worked and was fascinated by it. It was at least 3 months' work going through all the geometric and mathematical equations, trying to work out how it actually does this, to finally produce a computer program which is now part of ridethegeartrain.com. There's a special button there you can click for polygon cutting. And I'll demonstrate this and show how it makes different shapes. Okay, I'm going to get straight to the nitty-gritty and show you how polygon cutting actually works. And to do this, I've got a simulation of the polygon cutter on Ride the Gear Train. If you scroll past all the lathe-related stuff and go to near the bottom of the menu list, we'll find Polygon Cutter Generate Images. Just click on that, and we come up with a whole lot of help messages and stuff and instructions about how it works. But the simple thing is just to reset all the data to the default settings, and then click Run, and we'll see. Here we are. So here you can see we've produced a hexagon, and you probably got the idea that the tool is rotating around a piece of work which is also rotating. And this is something similar to planets going around the sun, with moons creating circles within circles. And it's also similar to the spirograph toy that we used to play with. So this has 6 pedals, and if you look closely at the center, the secret is in the center of the donut. And here we have the center here zoomed in, and you can see it's got 6 sides. Now what this computer simulation does is it has to use iteration to keep adjusting the polygon until the apices or apex of each corner is just touching the circle which represents the piece of metal that you're cutting. I've used the terms apex and vertex interchangeably, and sometimes called it a corner to try and keep it simple. The correct term actually is vertex for the 6 vertices on a hexagon, and the highest one may be called the apex. The next thing we want to know is how much curvature there is on each flat. That was one of the questions that was asked online. Just how flat are these sides? Well, I set about calculating the answer, and it turns out to be not trivial, but this is all the data that was entered. And here we calculate on this line here indentation. That is how much indentation there is at the center of the flat. Now, we gave the radius 10 millimeters, and so this is measurement is in millimeters. So the indentation is 0.192 millimeters, which could be expressed as a percentage of the width of the flat, as 1.9% of the width of the flat. Another way of representing this indentation is what circle would fit into these 3 points, the 2 corners and the center of the flat. And it's a 64 millimeter radius circle. So the sides are actually quite flat, and of course just by looking at the diagram you can see that these sides are quite flat. So that's quite a good example. You can see here that it took 222 iterations to get this, and that's because there are 2 nested loops, one inside the other, and it's difficult to make it converge. So that's the basis of the answer. Let's go back to Polygon data entry page and try some different things. Now, M is the number of tools on the rotating tool cutter. The next item is G for gear ratio, how many turns the tool cutter does for every turn of the chuck. And if there's only one tool, this generally equals the number of sides. So we could say, maybe, should we have a look at 12 sides? This tells us whether it's rotating clockwise or anti-clockwise, and W represents wiseness of the term that I made up. And this is the radius of the metal that we're cutting. So if that's in millimeters, then all the other measurements will also be in millimeters. D is the ratio of the radius of the cutter divided by the radius of the workpiece, which is also the same as the ratio of diameters. So the rotating tool is 4 times bigger than the piece of metal, so it would be 40 millimeters. You can also enter the 40 millimeters directly if you want to, and of course if you already have a tool you'll know that it's measurement and you can put that in there directly. The DOC is depth of cut, and that's one of the iteration loops. It has to work out the depth of cut required so that the apex of the hexagon actually lies on the circle that we're cutting. However, if you have a specific depth of cut that you want to look at, you can enter it in here. And next we've got the number of the degrees with each step. If you have a small degree step, it'll make the curves look smoother. And this is the amount of time delay on each step. We've got it set at a fairly short time delay, so it runs quite fast. But you can set it to 0, of course, and it'll run at full speed. And you can adjust the captions on the graphs, and those are preferences. You can turn it on and off. Okay, so we've just run through all the input data. Let's run it. So we're getting our 12 sides, and you can see in the close-up the 12 sides, and the apex is right on the circle, so the iteration did converge. And in this case, 127 iterations. The flatness is 0.067 millimeters in the middle of each flat, which is 1.3% of the width of the flat, or a radius of 49 millimeters. And that's all the data we just entered. Return to the Polygon input page and do something even more interesting. What if we have a gear ratio of 13 and we've got 2 cutters on the tool assembly? You'd expect this to make 26 sides, so let's run it and see. And it says the number of sides was 26, and the flatness is 0.015 or 0.6%, 48 millimeters radius. Now, estimating the number of sides when you've entered M and G is a little complex. If you have an even number for G, M divides into 12. What happens is it starts retracing over the tracks it's already made, so you only get 12 sides instead of 24. Let's run that and check. "12 sides." So actually calculating the number of sides from the parameters you've entered is not trivial, but the program does it. Uses a slightly complicated algorithm to figure it out. Let's try 4 tools at, I don't know, 17. Let's make a really complicated looking one. Now this one really looks like a donut, and we've got a little error message that says that it couldn't converge. Just there's so much data in there, it just couldn't actually converge. But just using an estimated depth of cut, this is roughly what it looks like. It's almost a circle with so many flats. It's got 68 sides on this. I think it just looks nice and pretty. Once you've chosen your gear ratio, you can also use Ride the Gear Train to tell you what gears to place in the gear train or gearbox settings to give you the required ratio. Instead of choosing an imperial thread or a metric thread, you scroll all the way to the bottom and find the Polygon cutter adapter, and that will allow you to enter a gear ratio and calculate an equivalent thread. I'll go over this process in more detail right at the end of this video. So let's look at the actual mechanism used to drive the rotating cutter. The key is that the cutter has to be synchronized with the spindle or chuck. So if we had looked at a G value or gear ratio of 4, the cutter would be turning 4 times faster than a chuck. And if you only had a single tool on it, it would make a square. Most people use the lead screw to drive the cutting tool. This is particularly convenient because the gearbox, thread cutting gearbox, and gear train can be used to adjust the gear ratio fairly easily, and certainly gives a wide range of gear ratios as well. The rotating tool is mounted on the tool post here and is connected to the drive mechanism with a drive shaft with universal joints on both ends so that the carriage can be moved backwards and forwards like this. To make the rotating cutter head, they used a milling attachment on the lathe with a dividing head to rotate the work around. MakeItExtreme did demonstrate how this works by putting a pen in each of the tool holders and showed them marking out the hexagon on the work that was to be cut. But we can produce something like this with the much steeper sides. This one has a gear ratio of 2 and 3 tools. So 2 times 3 gives 6, so we have 6 sides. But with these very narrow, tall loops, we see that the sides on the hexagon are almost dead straight. This is an interesting pentagon that we're producing with a 5-sided star, 5-pointed star, and it has 5 cutters and a gear ratio of 2.5. And you can have fractions like this, but you have to convert them into an integer, so it would have to be multiplied by 2 to give 5, and you expect 5 times 5 to give 25. But since it divides unevenly into m, it overlaps, and it only gives you 5 sides. So that's a rather interesting one. This is an interesting variation. We have a gear ratio of 2.5, the same as before, but we've only got 2 cutters. That 2.5 has to be multiplied by 2 to give 5, and 5 doesn't divide evenly into 2, so we take 5 and multiply it by 2 and get 10, and it produces 10 sides. In this case, we have 3 cutters with a gear ratio of 2.5. Again, 2.5 has to be made into an integer, so we multiply it by 2 and get 5, and 5 times 3 is 15, so we get 15 sides. In this case, we have 15 cutters, and the gear ratio has gone up from 2.5 to 3, so it's already an integer, and we leave it alone. Since 3 times 15 is 45, we might expect it to make 45 loops. And actually it does, but because 3 divides into 15 5 times, it tells us that it's going to overwrite itself, actually 3 times. So we ignore g equals 3 and calculate 15 sides. Treat g as though it's 1. In this case, we've got 3 cutters, and g is 1.75. Now to make that into an integer, we look at that as being 1 3/4. That's 4/4 plus 3/4 is 7/4. That's 7 over 4, and to make it into an integer, we have to multiply by 4, and we get 7. So g is now 7, and 7 times 3 is 21, and we get 21 sides. This one's a bit simpler. We take g of 2.5 and multiply it by 2 to get 5, and 5 times 6 is 30, so we get 30 sides. Here we have 16 cutters, so m is 16, and g is 3, and 16 times 3 is 48. And since 3 doesn't go evenly into 16, we don't have to modify it, and we get 48 sides. In this case, we have 3 cutters on the cutting head and a gear ratio of 3.1. And to make that into an integer, we have to multiply it by 10. And so g becomes 31, and 31 times 3 is 93. And we get 93 sides. Now, if we really want to use up a lot of ink, we have a gear ratio here of 1.1 with 16 cutters. 1.1 multiplied by 10 is 11, and 11 times 16 is 176, and we get 166 loops. In this interesting variation, we're actually making little flutes on the side of the work, so it comes out as a fluted shaft instead of really being square. The specifications for this square are very similar with 4 tools, but they are rotating anti-clockwise instead of clockwise, making a bulge. The program calculates the indentation, but in this case is a negative number bulging outwards by 1.4 millimeters in the center of a flat. 4 tools cutting an octagon, and here a single tool producing 100 loops. As you can see in these examples, the lines that are produced are not straight lines, they're slightly curved, sometimes concave and sometimes convex. And people have asked, how straight are those lines? And I wanted to answer that question. I tried using algebraic methods. Unfortunately, it reduced to a quadratic equation which was transcendental and could not be solved, so I had to resort to numerical methods by iteration involving 2 loops. I did find that Tony Foale had done a really good analysis of this problem, both mathematically and using this cardboard model, and demonstrated how 2 rotating objects could produce a line that's almost straight. However, I still didn't feel fully satisfied that I knew what kind of shapes it was drawing. This is the geometry that Tony worked out, and he used that to derive the equations necessary to describe the motion of the cutting tool. And that is what I used in Ride the Gear Train, converted into PHP code here. I won't go into any more detail with that, as it's all described in the help files of Ride the Gear Train. I will briefly mention that the iterative process used the Newton-Raphson method, and I needed an initial estimate of the depth of cut. So I ran the program several times with different depths of cuts and plotted it against the number of sides and derived an equation which gave me the initial estimate. This was done by curve fitting using log of the depth of cut against the number of sides. I had considered making a polygon cutter myself, and one way you could do that is to make an electronic lead screw mechanism and use that to drive a stepper motor mounted directly on the tool post. That would be a nice way of doing it. The electronic lead screws are described on Ride the Gear Train as well, and they work by having a counter mounted on the spindle that counts how many degrees it's rotated through, and that counter is fed into a computer which then calculates how many turns need to be applied to the lead screw in order to produce any particular thread. And that same system could be used to rotate the tool for cutting polygons. However, I've recently made a milling attachment for my lathe, and that proves quite successful in making hexagons, as you can see in this video. So now we're going to try using 4 cutters with a gear ratio of 15 and see what that looks like. Now, the pattern that you'll see being developed here, you can imagine being used as an engraver for engraving purposes rather than cutting polygons. So if you have a piece of metal and face the surface off and then use an engraving tool to follow this pattern, you'll end up with this interesting pattern on your surface. So that's another application of this program, completely different from forming polygons. These types of machines have actually been made. These are known as guilloche machines, and they are used to do engravings on watch faces, but they've also been used to make complex patterns like this on banknotes. If you look at the help files for Ride the Gear Train under polygons, you'll find links to several different articles about these types of patterns. They are described in Wikipedia as being Rosetta orbits, also in the class of epicycloids and hypocycloids. On my help files you'll find a link to a YouTube by ClickSpring about these types of patterns. Now let's go to preferences. You'll find those at the bottom of the list of all the data we've been entering, and we'll just turn off the long instructions now that we're now familiar with how to use the program. It'll look a bit cleaner if we just turn off all these instructions. We're going to try pretty much a standard option with 6 cutters and a G value of 1 going anti-clockwise. Work size is 10. Diameter of the cutter is 2 times the radius, or otherwise 20. Let's go by 20, by the absolute size of the cutter is 20 millimeters and the work size was 10 millimeters. Actually, we normally use 40 here, so we use a tool size of 40. There's the diameter of the spinning cutters, and we put in a blank for depth of cut so that it'll calculate for us. And there's a fairly standard looking hexagon, slightly convex, this one. So it says here that it's convex, and that means our flatness calculation is a negative number. It's bulging outwards instead of inwards by 0.255 millimeters. Now let's go back to our data entry again. And actually what we've usually been doing is using a single cutter with a gear ratio of 6, which also gives 6 sides. And we'll see how that compares. Now we've got indentation, so the flatness calculation says plus 0.192, and it's described here as being concave. What happens if we use a mixture and use 2 cutters and a gear ratio of 3? It's still going to give 6 sides, and see what that looks like. Oh, that's even a little better. Slightly concave. It says it's concave, but the indentation is only 0.082, so it's about half as much indentation. What happens if we have 3 cutters with a gear ratio of 2? How does that compare? Oh, that's even better. Look how straight those sides are. Now we've got convexity of minus 0.014 millimeters, almost dead flat. So that appears to be our best option. What happens if we use a cutter that's a bigger diameter? Perhaps we'll go to say 100 instead of 40. And when we run this, we'll see that the axes get changed to suit the size of the image. And now we've got almost dead vertical sides. Pretty amazing, really. And it's considered convex, but it's only 0.002 millimeters from being flat. So that's almost perfect. Now I've been doing some experiments to make a 6-pointed spline, and here's an option I came up with, having 6 cutters on the rotating tool with a gear ratio of 1 going counterclockwise, and as usual the work size is 10 and the diameter of the rotating cutter is 26 millimeters, and the depth of cut is 4, which I obtained just by trial and error. And let's see what we get when we run that. So there we can see on the zoomed in picture on the right hand side how we could end up with a shaft which is sort of like a spline. There's another spline I made here using M of 6 and G of 0.25 with a cutter that's 20 millimeters and a depth of cut of 3. Run that. That's kind of cool. It's not such a deep spline as we had with the previous one though. Here we can see a pattern that makes a simple groove or flute along the side of our round blue shaft, and we can adjust the depth of that by altering the depth of cut, and that's done with a gear ratio of 1 and 1 cutter, the cutting diameter of 20 millimeters and a depth of cut of 5 in order to produce that one flute. So what happens if we experiment with that a bit and do the same thing with, say, 4 cutters? Now we've got 4 flutes, and we could alter the parameters a bit to make them join up together. So now we have 8 flutes separated by little gaps, and that was simply by increasing the number of cutters from 4 to 8. And now in this case we've made a 4 fluted shaft, and I've achieved that by using 4 cutters with a gear ratio of 1. The cutter head has a diameter of 50 millimeters and the work size is 10, so the ratio of 1 to 5, and so D is 5, and the depth of cut is 4.8 by trial and error, so that the tips of the flutes end up on the circle. Now we're going to try something different. We'll have a piece of work that's 10 millimeters in diameter, but we'll make the cutting tool the same size, so the D ratio is 1, gear ratio of 1 with 3 cutters, and so it gives a triangle with curved surfaces. But if we look at the left hand image, we zoomed out, we see that the motion of the cutters is a perfect circle. So here we're going to do another one with 5 cutting tools and a gear ratio of 1, and also going anti-clockwise as usual, and the tool size is going to be 4 times the diameter of the work, and we'll see what that looks like. So what's interesting about this one is not only that we've produced quite a nice looking pentagon, but also the tool is rotating in perfect circles with this gear ratio of 1. Now that we've looked at the effects of gear ratio and number of cutting surfaces on the tool and how it affects the number of sides, we can now look at exactly the same thing occurring when you cut internal holes with lobes, a number of lobes being equivalent to the number of sides. And to do this we need a small internal cutting tool with multiple edges, and you can see here that Eugene has done a YouTube video using some homemade tools with 2 cutting edges or 3 cutting edges or 1 cutting edge. And as I say, the same rules apply for working out how many lobes the hole will have when he uses this. And in his videos you'll see gear ratios shown which again fit with our model. So here he's using a gear ratio of 2 with a single lobe cutter, making 2 lobes in his shape. And this is sped up 2-fold. 2.5 is the gear ratio, and he's using a single cutter. 2.5 has to be multiplied by 2 to make an integer of 5, and you end up with 5 lobes. Next he has a ratio of 3 with a single cutter, and that'll give 3 lobes. Next we see a gear ratio of 3.5 has to be multiplied by 2 to make an integer, so 7 is the number of sides this should have, or number of lobes. Now switching to a 2-point cutter, so M becomes 2 instead of 1, and the next ratio is 1 to 2, multiplied by 2 will give 4 lobes. So we now have M is 2, or 2 cutters. The next gear ratio is 3 with 2 cutters. That'll give 6 lobes. Now switching to a 3-point cutter, which means M will now be 3, and a 1.5 ratio multiplied by 2 is 3, and 3 times 3 will give 9 lobes. Next gear ratio is 2 with 3 cutters, should give 6 lobes. The next gear ratio is 3 with 3 cutters, should give 9 lobes. Before going on further with this, I'd like to also show you something else on Ride the Gear Train on the main menu. If you're running Ride the Gear Train for the first time, this is what you'll see. And this is an introduction mainly to let Google know what the program's all about. And here's a quick start guide, which we'll be using this time, because what we're doing is basically the same as cutting a thread, but we're telling it to make a thread that gives the required gear ratio for polygon cutting. So you run the polygon simulator we've been looking at and decide what gear ratio you want, and you enter it in this program, and it tells you what gear train to use. So we have to start by telling it what kind of lathe you're using, and this is just the same as screw cutting. I like to use my Boxford with a Norton Imperial gearbox, so click that one, click return. So that's selected the lathe and entered all of its lathe specifications. Design the gear train. We'll use not just 0 compound gears because it doesn't give you too many choices. I prefer to use 1 compound pair, and this is a diagram of what the gear train would look like with 1 compound pair. You can ignore these 3 gears at the top because they're just for reversing, and it is designed so that the stud gear turns at the same speed as a spindle, and so it can be considered the first gear, the stud gear. Then we have a pair of compound gears which are physically joined together, and they're driving the lead screw gear. So that's what we mean by 1 compound pair, is these 2 are considered a pair. Return. Scroll back down a bit further. Next question was, are you going to use automatic? Well, for most applications we'll use automatic. There's only a few lathes around, like the Boxford, that has a special set of gears for doing compound pairs, but most of them use the standard change gears for making up compound pairs, and the program will automatically put together every possible combination. So the next thing is enter the gears that you have, so it'll need to know what choices you have for your gears. You might say have a 100-tooth gear as well, so add that in, press return. So we've got our gears. This gives you a summary of what's actually in there. And then the calculation type. Well, normally you'd choose, say, a imperial thread and click this box. In this case, we go past the metric thread here, carry on right all the way to the bottom, and we find one for polygon cutter adapter. And we make sure we've checked that and click return. So that set things up, and the next thing we need to do is tell it how much error we're willing to accept. Well, for something like this, if you had a little bit of error, it would really mess it up, so we'll only want 0% error. And finally we get to put in the gear ratio we want. Let's make it 5 for the gear ratio and see how we get on. So we now return to the menu again, and finally once all the data's in, you can click run. But the advantage of using all these separate buttons is that if you want to come back and alter something later, you just click whichever button you want to change, and you don't have to go through the whole works. So we have a results summary here, which shows 25 results and 0% error, and it requires a 1.6 thread per inch thread to make the lead screw turn 5 times faster than it would for an 8 thread per inch. And the simplest one here is using an idler gear between the two, and so just a 100-tooth gear on the stud gear position and a 56-tooth gear in the lead screw, and more or less anything in between will give you the right gear ratio. If we draw that, we can see what it looks like. Using gearbox code A1 and 100 teeth on the stud gear, an idler gear of any size to make it fit on the gear train, and a lead screw gear of 56. Now it's possible you can't fit such a big gear on the stud gear, so in that case you may have to go back and try again. Well, here's one better with 40 teeth in the lead screw position, and 20 and 100 as a compound pair, and 56. We do have a problem here because the second compound gear, compound 2, has 100 teeth and overlaps with the stud gear, so this it would hit the shaft of the stud gear. So we need to do something to prevent that. And so the program tells you what to do. It tells you to put in an idler gear in here. So if you put an extra gear in there, it'll allow these two to connect together, as long as they'll fit on your gear train. So these diagrams can be quite helpful. So that's how you use Ride the Gear Train to recommend a gear train that's going to give the required gear ratio. I will place the links and credits to all the people who have contributed to this video, including Eugene in this last set, and MakeItExtreme. And special thanks to Tony Foale, who provided the geometry and equations that are behind this program. Very important aspect of it. So thank you, Tony.